Hey there everyone. In this video we're going to be talking about properties of logarithms. So using these properties will help us maneuver them around and help us solve more intricate equations. All right, so let's take a look. We have log base b of b. What is that? Well, we know that it is the exponent on b that gives b. What do I raise b to get b? Well, it's 1. Wha-bam! There's our first property right there. Log base b of b is 1. And that works for any positive b, right? What about this one? Log base b of 1. What does that equal? Well, b to the what equals 1. So b is a positive number. What do you raise a positive number to get 1? It's always 0. That always works. And by the way, another way to see that is to think about the graph. The graph of a logarithm, when you plug in 1, it always gives you 0. See right there? That's the x-intercept. Now we have some nice properties. These are called the inverse properties of logarithms. And this is how they interact with exponential functions. So if I take b and raise it to the power log base b of x. So I put log base b of x as an exponent on b. What does that give me? Well, let's think about it. What is log base b of x? Remember, log base b of x is the exponent that you put on b to get x. By definition, that's what log base b of x is. It's the exponent on b that gives x. Well, look what I did with it. I put it on b, so it must give x. There you go. And you can do it the other way around too. You can do log base b of b to the x. So here I'm plugging b to the x into the logarithm function. So log base b of something, well that's the exponent on b that gives this something, right? So b to the what equals b to the x. Oh, it must be x. So again, it does the same thing. These are called the inverse properties of logarithms. Now, inverse of what? Well, this is telling us that log base b is the inverse of b to the x. So you see, if you plug the inverse function into the function, you just get x back. And vice versa. If you plug a function into its inverse, you just get the x back. Why does that make sense? Well, the inverse just does the opposite of what the function does. So if the function takes you here, you take x and you get f of x. Well, the inverse function goes the other way. It takes f of x and gives you back x. So if you plug f of x into the inverse function, you get back to x. Right? So that's what's going on. B to the x and log x are inverse functions. And you may have noticed their graphs look quite similar, right? There's a nice comparison between the graphs. If I graph b to the x, it looks like this. If I graph log base b of x, it looks like this. And if you know something about graphing inverse functions, you know that to graph the inverse function, you just reflect the graph along the line y equals x. So if I just imagine that was a mirror and I flipped this curve, reflected it across this diagonal line, guess what I get? I get this curve. So they are indeed inverse functions. And that's why they have this property that when I plug one into the other one, I just get back to x. It's just making this go in a loop. Right? So these properties are going to be very useful in helping us solve equations. Because when we have an equation, we're going to apply a logarithm, or maybe apply an exponential function, and then try to get a solution. We want to solve for x. Okay? Now, you might, just through investigation, be able to spot what the answer is. But let's try to use these properties to get the answer. Remember that logs are inverses to the exponential functions. So here I have an exponential function with base 2. So to undo that, I'm going to apply the inverse. So I'm going to apply log base 2. If I do it to the left-hand side, I also have to do it to the right-hand side. So I'm going to take log base 2 of the left-hand side and log base 2 of the right-hand side. Well, what is log base 2 of 2 to the x? Well, that was our inverse function. Log base b of b to the x is just x. So log base 2 of 2 to the x is just x. Look at that. I got x equals. So x equals log base 2 of 32. So in other words, 2 to the what equals 32. Well, that's a 5. Right? It's log base 2 of 32. Now, that would work even if we weren't able to get a nice whole number here. Because you may have noticed, well, that's just the same as what we had over here. Like, is that really useful? Well, it is. It is. And this will explain why right here. So if I had the equation 7 to the x equals 8, and somebody asked to solve that for x, well, now you can't just through observation, you know, pick off that that was a 5, right? I mean, here you could, but here I don't think you can think of what the x would be. So we'll do the same thing. I'm going to take log base 7 of both sides, and because these are inverse functions, that just becomes x. And so my answer is this. X equals log base 7 of 8. And that's how I would write my answer. Just like the answer up here was 5. Here we were able to simplify this and just get an integer. Here you can't do that. It's like when you take cubed roots, right? Sometimes if you take the cubed root of something like 27, you can get a nice integer. But other times when you take the cubed root of something like 9, you can't simplify it. You just leave it like this, right? So that's the same thing that's happening here. Sometimes you can actually compute the logarithm and get an integer answer. Sometimes you can't, so you just leave it like that. That's the simplest form. Let's do another one. Okay, well, I got to get the x out of the exponent. What will I do? Well, what were we doing? We're applying the inverse function. What's the inverse function to e to the x? It's log base e. What do we call log base e? We call it ln, the natural log function. So I'm going to take the natural log of both sides. These are inverses, so that becomes x. And there's my answer. X is the natural log of 19. There's no way to simplify this any better. 10 to the x equals 3. I got to apply the inverse function. What's the inverse function to 10 to the x? It's log base 10. What do we call log base 10? Just log, right? So I'm going to take the log of both sides. These are inverses, so this gives me x. So there's my answer. X is log of 3. All right. Well, let's look at this one. Here we have logs at the beginning, and I want to get rid of the logs. Well, what can I do here? Well, I can use the other property. Remember, that wasn't the only property that we had. We've been using this. We've been taking the log and using the fact that the log of b to the x is just x. But look at this. I also have this one. If I have logs, I can put them as an exponent on b and get x. So that's what we got here. We have logs, right? So what I can do is write them as exponents on the base, which in this case is 3. So see what I did? I made these exponents and put them on 3. Now, where can I go from here? Well, these are inverses, right? 3 to the x and log base 3 of x are inverses, so that just gives me x. Okay, so is my answer just this? Well, yeah, but we can simplify this. Remember what log base 3 of 14 is? Log base 3 of 14 is the exponent that you would put on 3 to get 14. Right? That's by definition what this is. It's the exponent on 3 that gives 14. Well, so if I put it on 3, I must get 14. Another way to think about that is, again, these are inverses, so they kind of cancel each other out, right? Inverse functions cancel each other out. And also what we're seeing here is the one-to-one property of logarithms. If we write this in a little more general form, if I write log base b of x equals log base b of y, I can do the same thing. I can put each side as an exponent on b. The b's and the logs cancel. I get x equals y. And of course it works the other way. If x is the same as y, then of course their logs are the same. This is called the one-to-one property of logarithms. We had a one-to-one property of exponential functions, and we also have a one-to-one property of logarithms.